All right, introduction to bubble sort. Welcome to Introduction to Bubble Sort. Bubble sort is a fundamental sorting algorithm that, despite its simplicity, it holds a significant educational value. So, at its core, bubble sort operates on a very straightforward principle. Uh, it basically compares adjacent pairs of elements in an array. And if a pair is found in the wrong order, that is, if the first element is larger than the second, they are swapped. And this process is repeated over and over, traversing the array multiple times until no more swaps are needed. And that indicates the array is sorted. Uh, you can think of yourself organizing a row of books by their height, and where you only compare and swap uh, two books adjacent to each other at a time. So you will start from one end of the row and move to the other. So if on a complete pass you make no swaps, then you know the row is organized. I hope this analogy helps you understand the bubble sort process, since it closely mirrors how bubble sort works. Uh, the reason why it has name bubble sort is because elements bubble up to their correct positions through a series of swaps, similar to bubbles rising to the surface of water. The beauty of bubble sort lies in its simplicity and the intuitive grasp it offers on the sorting process, making it an excellent starting point for beginners to understand algorithmic thinking. However, you also need to recognize bubble sort's limitations. Due to bubble sort's basic approach, it isn't the most efficient algorithm for sorting large data sets. So, but the good thing about bubble sort is its stability. What we mean by stability is the sorting algorithm maintains the relative order of equal elements. Now let me go to the next slide. Yeah, this is the bubble sort pseudocode. So you want to repeat this process until there is no swap. And for each pair of adjacent elements, if left is greater than right, you want to swap those elements. Working principle of bubble sort. So if we kind of look into the mechanics of bubble sort, we can visualize its operation step by step and see that it is very simple. So the algorithm kind of begins at the start of the array and compares the first pair of adjacent elements. Say if the first element is greater than the second, then the swap will be performed between the first and the second element. By performing this swap, it ensures the larger of the two moves one position to the right. And this comparison and swapping process continues for each pair of adjacent elements along the array. So this way, the largest unsorted element kind of bubbles up to its correct position at the end of the array by the pass's conclusion. So it will do that one pass, but the algorithm wouldn't stop there. Uh, what bubble sort does is it restarts from the beginning of the array for another pass. But this time, because we know that the largest element bubbled up to the end of the array, we will ignore the last element, which is because it's now correctly placed. With each pass, the unsorted portion of the array diminishes by one element, and the process repeats until no swaps are made in a complete pass. And if no swaps are made in a complete pass, then this means the array is sorted. Analyzing bubble sort's efficiency. So um, now, so we looked at how bubble sort works. Now it's important to understand its time complexity and space complexity, uh, so we can understand the algorithm's efficiency and performance. So at its worst, the bubble sort exhibits a quadratic time complexity, which is O of n squared. And we know that n represents the number of elements in the array. And this quadratic relationship stems from the algorithm structure, uh, because the algorithm requires a series of nested iteration. And for each element, the algorithm has to make a pass through the remaining unsorted elements. So if we were to talk about the worst case scenario, that's when the array is in reverse order. That means we need to have the maximum number of swaps for each element to bubble to its correct position. But the good thing about bubble sort is in the best case scenario would be would be the case that array is already sorted or almost sorted. Then bubble sort can terminate early. So it will have the best case time complexity of O of n. And this would be possible if we implement the optimization of checking for a pass without swaps, which we will talk about more. Space complexity. Yeah, let's now talk about space complexity. Uh, Bubble sort can operate in place, which means bubble sort requires no additional storage beyond the input array. So we achieve a space complexity of O1. So if you want a space efficient sorting choice, bubble sort would be a great candidate, but the time complexity in larger data sets, since the time complexity of the worst case and average case is n squared, you wouldn't want to use this in large data set. So let's talk about practical considerations. So we've seen how bubble sort works, and it's conceptually very simple and has educational value. Uh, Bubble sort isn't really used in real world application due to its time complexity being of n squared. For average and worst case scenario, this This way, its use is only confined to small data sets or for educational purposes. What good thing about bubble sort is uh, it has a stable nature. So there's a stability in sorting. So if you would like to use an algorithm that is stable and preserves the ordering, then might want to consider. So optimization of bubble sort, we looked at the pseudocode before. That wasn't the optimized version because it repeatedly traverses the array and swaps adjacent elements if they're in the wrong order. And this approach does not account for the possibility that the array may become sorted before all passes are completed. So in order to address this inefficiency, you can introduce a Boolean flag to your algorithm named has swapped. So what this has swap does is it monitors the activity in each pass. And if we find that a pass completes without any swaps, uh, it will signal that the array is sorted and the algorithm can terminate early because we have this while loop. This optimization can significantly reduce the number of passes in a case where the array is nearly sorted or sorted. So once you have this, the best case scenario where the algorithm time complexity will improve from O of n squared to O of n, because when array is sorted, um, if we use this optimization, then only one pass will be necessary. So here is a Python code for bubble sort, and you can see that the optimization is already implemented. And here is a Java code for bubble sort. So we talked about best, average, and worst case scenario. So to really understand the best case scenario, that's when the array is already sorted. This means with the optimization, the bubble sort just need to make one complete pass without swaps to verify orderliness. This means we will have the linear time complexity of O of n. Uh, on average case, when we mean by average case, it assumes a randomly ordered array. Uh, bubble sort tends to show the algorithm's quadratic nature. So it will have the time complexity of O of n squared. And then the worst case is when the array is sorted in a reverse order. This means that the maximum number of swaps is required so that every element has to bubble all the way through the array to find its rightful place. Bubble sort versus other sorting algorithms. So we want to kind of position bubble sort in the broader context of sorting algorithms. So when we kind of compare bubble sort to other simple sorting algorithms such as selection sort and insertion sort, we find that they all share a similar time complexity of O of n square in their basic forms. However, each sorting has its unique characteristics. Uh, just to give a brief example, so selection sort will consistently perform O of n square comparisons. Doesn't matter what the input looks like. And insertion sort will uh, do really well with nearly sorted data, similar to optimized bubble sort. And as we transition to more sophisticated algorithms like quicksort and merge sort, uh, we can see the stark difference. So quicksort will cover more in quicksort lecture, but with its divide and conquer strategy, offers an average time complexity of n log n. Uh, though in the worst case, the time complexity uh, can degrade to O of n square if pivot is not chosen wisely. But n log n compared to n square time complexity in bubble sort is really good. And if we talk about merge sort basically guarantees a O of n log n time complexity. However, you have to pay for the extra space for temporary storage. So as we delve into other sorting deeper, you will understand uh, more of bubble sort simplicity and stability, but you will see the limitation in the scalability and efficient of the bubble sort algorithms. Thank you. Let me stop the